Okay, let's start class. We are a little bit late. So yesterday, we reviewed linear algebra, which you learned in high school, right? So you already learned about Gauss elimination method in high school. So today, I'll just introduce several concepts. This is mainly concept. But most of the things, I assume actually, you actually learned in high school. So what I'm explaining today is I try to explain a little bit more formally. But too formal, it's not too easy to understand. So if I teach this class to mathematics department, I'll teach very formally, but we are engineering, right? So most cases, I'll explain using examples. So topics I cover today is just linear equations in row picture, column picture, and vectors and matrices of spaces. So Yang Seung-ho, in high school, right? You learned about vectors and matrices as well, right? So actually, it's nothing new. Let's move on. Okay, these things I just handwritten last night, rather than just writing in front of you. So here, this is just linear equation, right? With the two variables, right? So Hyun Sang-won, you know how to solve them, right? You know how to solve them, right? So this is dimension 2, means two unknown variables. Here we have two equations as well, right? So this is representing as an equation. This part is we are representing in matrix form. Ji-young-tak, are you familiar with this form? Yes. So we already know, so we don't have to explain that, right? So we already know how to multiply matrix with vectors, right? So actually, both are equivalent. We just represent differently. Okay? So in that case, we just call AX times B. Most cases, actually, we just make A bold. Even X is vector, actually. Sometimes we just make it bold. Sometimes you put hat on top of that. Like sometimes a vector, you just sometimes represent this way. Some other people say, okay, I just present this way, or some people this way, right? For this class, I just ignore this head or bars. Okay, but in the context, we'll understand what scalar, what vectors, right? So sometimes you can say, okay, this A is more or less bold, say is matrix. Sometimes we say, okay, X is B is a vector, right? So this is very simple notation for the equation. During my lecture, if you have any questions, just please raise your hand. Then I try to describe a row picture. This is just English. But drawing this line representing in geometry, you know that, right? Kim Won-jun. When we have two equations before, right? Then we try to show these two equations graphically. So this is a graphical representation of those two lines, right? Yes. So how could we know that, right? So I don't have to explain. So basically, one line represents each equation, right? So every point in blue line satisfy this condition, right? So every line, every point red line satisfy this condition, right? Point which intersect point of both lines satisfy both equations. It means there's a solution which satisfies both equations, right? So this is the way you can show it graphically. Okay? So when you have two equations, we can solve them. Means we can find unknowns which satisfy both equations, right? So this is a special case actually. This is the normal cases. Both lines intersect. Hyung-tak, can you come with some other example whether two lines do not intersect? Right, they might parallel, right? Yes. So sometimes you can say this one line, the other line is like this, right? They never meet. So they don't like each other, right? They just go in parallel, right? So in that case, Hyun-sang-won, do you have any solution? No solution, right? Then how about both lines, both equations are correspond to the same line? You may say, okay, this is line. It says, oh, this is one line. Oh, the other line is exactly the same.
They love each other, man.
Right? Just they got married, right? So in that case, how many solutions do you have? Infinite, right? So when you have linear equations, always is just one solution, or no solution, infinitely many solutions, right? Okay, it's pretty easy, right? So this is one way you view it. Still, on this line, we never use the concept of vector at all, right? So next diagram says we call column vector. This is more way, just we represent the matrix differently. Here is actually, you see the difference between two, right? This is equation, right? 2x minus 1. Now actually here, we'd rather see, let's say, this one and this one separately. Previously, we saw this is row picture. Column picture is more or less we view this way. Okay? So, this is another way to represent. Because there are two vectors, you can say one is U, one is V, right? There is a linear combination which makes B vector. Okay, so Ho-Juan, you know how to represent this vector in these two-dimensional spaces, right? This XY axis, whatever, right? So this is a way you can represent U, because U is in x-axis is 2. This way is minus 1. So this is U vector, like 2, 1, this is vector. This representation is U, right? This is more or less geometrical interpretation of vector. Okay? Then another is V. 이상욱. What is vector? If you can explain in Korean better, then you can explain in Korean. It's okay. It's magnitude and direction, right? Scalar has only magnitude, right? Let me ask a question to Lee Sung-tae. Number 3, is it scalar? Let's say 156 is bigger or smaller? Sometimes what I'm saying is, Ihabin, when I say, how tall are you? 184. 하준수, do you have any idea? He said his height is 184. Do you have any idea? 184 millimeter? 184 kilogram? But really, when you think about the quantity, okay, some of the quantities, actually, unless you mention unit, really it doesn't say much about magnitude. 정민이, can you understand it? Like, let's say, how tall are you? He says, oh, 184. Then 184 millimeter? Oh, I'm 184. Yes, your intention was 184 centimeter, right? But unless you specifically mention unit, actually, I don't know how big or large or small or big or little. I have no idea. Yeah, mathematics number is number. But in reality, in physics, in any area, you have to come up with a unit. Otherwise, actually, you don't mean that much. Right? 천상원, so how much do you weigh?
67 kilograms.
So kilogram is important, right? When you ask weight to Hasangwon, he may tell his weight in pound, right? So unless you mention about this kilogram, he may assume as in pound, right? Because he grew up in the culture. So even when you talk about scalar, you think about this unit. Yes, when you represent in the equation, you never say that. Even x and y, even your solution come up with number 3.5, usually means 3.5 kilograms, whatever. So most of the times you have some units associated with that, right? Then we talk about the vector, right? Vector is magnitude with direction, right? What's the speed of car which are driving on that highway? I say 60 miles per second, right? That's speed, right? Is it vector or not? Scalar. What's the corresponding term in English, corresponding term in vector in English for speed? This is more or less a quiz, right? It's a velocity. Velocity always talk about magnitude and direction, right? So most of wind, when you listen to the weather forecast, right? They say the wind is blowing from east or west, right? Many cases two-dimensional, right? So 지형타 is two-dimensional is enough or not enough? Then like a tornado, right? It just move up, right? So you have to think about all these vectors. So most of the concept that you see in the mathematics, you will have to be able to explain that in physical terms. Just simply just remembering, following, it doesn't help that much. Okay? It's a vector, right? Vector has dimensions, right? So here actually, so one way to visualize, they say, oh, these three-dimensional vectors. Then you don't see unless you see in pictures, right? This is more or less diagrammatic way. When you show them in diagram, now you have a better understanding, right? Especially for two-dimension, it's pretty easy to understand that. So basically, we can say this is vector is a resultant vector, but combining these two vectors is linear combination. Then what proportion will provide whatever this makes? From previous example, we know the solution was what was the solution? Then here is actually this one is x is 1, is y is 2. So basically 1, 2, by adding them up graphically, diagrammatically, it will come up with this result vector, right? That's the way you can say, oh, now I can visualize it. Actually, here actually, so we need to find the values of x and y, which are scalar, right? Which combines both vectors, which result in these vectors we are looking for. Okay? It's too easy, Kim Yoo-chan, right? So when you have 3 dimension, when you have 2 dimension, it's here it's so nice diagrams, right? 3 dimension, oh, it's not that so nice. Let's think about this. This first equation, right? But it's 3 dimension, right? X, Y, Z 3 dimension, right? So when you somehow draw 2x minus y, what is that? Point or line or plane? So what is it? Eh? Plane, right? So basically, it's these things I try to draw, but this is really is not. Yes, you know, to specify plane. How many points do you need, Kim Won-jun? Then, to make a line, to make a straight line, how many points do you need? Just for straight line, you need 2 points, right? Point A and point B straight, right? So you need 2 points, right? To make plane, how many points do you need? 3, right? Then with triangle, then there's a plane which covers all these points, right? So here actually, like 2x minus y, then it happens when y is 0, then you can come out, just put in some numbers, then you can come out this space, which is not easy to show graphically, right? In a way, it's like this is one plane. It's okay, 3 points are specified, then I can draw the plane, right? So put in some numbers, you can come out first one. Or even second one, yes, you can come with another plane, right? You come with another plane. So it's several choices, right? 2 planes meet each other. Then what is intersection in that case? Line, right? Also lines may be parallel, planes may be parallel, they never meet, right? Or just collapse into same line, same plane, right? There's 3 choices, right? There is third one. Also, this is another plane, right? If they meet each other, then this is another plane here. Then somehow, I try to explain with this, right? So hinge here actually is more joint line, right? When you meet this way, then there's a single point with the table surface, right? Or this one parallel, it doesn't meet. These lines and planes are parallel, right? So when they meet, then we have specific one point, which is solution. But sometimes they never meet, there's no solution. Sometimes they meet as a line, or just make a plane, then there's infinite solutions, right? But so in this case, the solution is this, but it's very difficult to visualize. Yang Seung-ho, what happens if we have 9-dimension spaces? Can you visualize that? It's very difficult, right? So conceptually, yeah, 2-dimension is easy. 3-dimension, I can just live with that. But 4 dimension, 5 dimension, 10 dimension, I'm sorry. Sometimes you have to solve the problem with 100 dimension. Then we can imagine, right? So what it really means. Then this is another column picture, right? So you can now use three-dimensional spaces with 3 vectors, right? So you can combine these things, then you can come up with a solution, right? So column picture in a way is more visible, right? This is B. Up to now, any questions? So here we have concept of column picture and row picture. Also, I'm just still mentioning whether you have a unique solution or no solution or infinite solution. I try to explain graphically how geometrically explain what's the case when they're parallel or they meet or the same line or whatever, right? Okay. 지금부터?
저렇게 표현을 해도요. XYZ를 찾으려면 저희가 고등학교 때 배웠던 그 연립방정식 푸는 법밖에 없죠.
That's one method. So you may have several methods which might be computationally more efficient, but basic concept is the same. Okay, let's discuss that issue. Here is we are just representing all these modeling issues, right? So I like to ask question. So previous equation, as you said, we can solve this problem, right? Using whatever method you learned, right? So it's Gaussian elimination method, right? In high school you learned it, right? Yeah, 소거법? They never told whether it's Gauss or not, just 소거법. But you never heard about Gauss, but that's the one he actually invented. So, like what I'm saying is from this equation, right? This is A. Oh, sorry. This is A and this is B, right? Also, its equation is A, X is B, right? So we try to solve that, right? So we have specific values of B. Okay? So in that case, solution is X is 0, Y 0, and G is 1, right? The question is, can I solve this equation for every possible values of B vectors? In previous example, we solved AX equal B for specific value of B, right? The solution was 0, 0, whatever, 2, right? 0, 0, 1 or whatever, right? But B value of B might be changing. It might be different, right? So can you solve them for every vector of B? You already learned, right? Like when you have Gauss elimination, so you have to repeat. Okay, now different set of B, then do it again, right? Basically, let's see. then I'll explain later, okay, using this slide. For the, like, for example, ax is b, this is a scalar, right? Let's say 3x equals 6. You know how to solve them, right? Oh, x is 6 divided by 3, right? Or you can say, okay, this is more or less 3 inverse times 6 is 2, right? When you use notation, this is the way, right? For the matrix, oh, this is AXB. Oh, can you come up with a very similar way? Very similar, right? This is more scalar equation. This is more or less matrix equation, right? Can you come with A inverse? If you come with A inverse, that's easy. Then, oh, now is x, whatever, 1 is A inverse by B1, whatever this is another value, right? Or x2, maybe A inverse by B2. So whenever you have different values of B, because once you computed A inverse, now you can easily compute solution, right? So this is special case when you, like in the case, can you do this thing always? What happens if A is 0? This equation is A is 0. So basically what I'm saying is x, 0 times x is 0. So how many solutions of x? Infinite, right? How about the other case? 0 times x is 3. No solutions, right? So you can guess. Oh, we might have similar cases here as well, right? Right? So we know that, oh, if A is 0, then you cannot divide. Here means for certain types of A, I'm not able to come up with inverse of A. Okay? So when you have, if you can come up, you can say invertible, or you can say it's non-singular. Or you can say, oh, this is non-zero. You already know these things, right? From scalar equations, right? So this is very equivalent concept. So later we will discuss more formally. The other one is let's come up with this. Now it's in this case, are you assuming, okay, now it's okay. It's for all x, y, g. So you can combine this vector for all x, and y, and g, right? So then this is values of whatever is b1, b2, b3, which is b vectors, right? What's the possible values of b? Assuming you can come up with every combination x, and y, and g. Ihavin, do you understand what I'm talking about? Let's take a more simple example. Let's say vector is 1, 0, 0. The other vector is 0, 1, 0. Another vector is 0, 0, 1. Okay. Then in that case, it's more or less, this is x vector, right? This is x vector. This is y vector, more g vector, right? Now you are combining this thing is whatever using this, like whatever is a x hat plus b y hat plus g or c g hat. This is then for all a, b, and c, all combination. What does it mean? It covers all of the spaces, right? Right? So because you can have any combination, even the same thing. Only thing is basis might be different. When you combine all of them, actually it spans all of them. So we call them as a vector space. Probably you already learned about vector space in high school, right? So Kim Hee-ju, have you learned about vector space in high school? It is the concept. No? 진용식, 진용석. Have you heard about vector space in high school? Can you speak up? Okay, let's move on. You already know how to multiply vector matrix with vectors, right? So A, X, right? You know how to multiply them, right? So Yang Seung-ho, have you learned about the inner product? Have you 내적? In what's 내적? That's inner product or dot product. Kim Won-jun, can you explain what the inner product is?
Multiply numbers with
Let's try out. Actually, it's I know most of students here knows that, but have some difficulty in explaining, especially in English, right? So vector, right? Vector V or whatever, right? We have some operation, right? So when you V, then we know how to add V1 plus V2, right? Here everybody knows how to add them, right? Also, when you say V, then also you know how to multiply with the scalar, right? 2, then twice. If C is 2 and twice, then minus 1 is the other direction, right? Then based on that, now you can say, okay, now I know how to do this. Right? This is more or less linear combination, right? You know how to multiply with scalar, then we know how to add them. Basically, now we know how to combine them using linear equation, right? Then this is defined, or this is addition of scalar and vector. This is addition of vectors. These are defined, right? What other operations are you interested in? Hajun-soo. Like in arithmetic of numbers, right? You have what? Plus, minus, divide, and multiply. Right. So, like here, 4 numbers. Then here, like between like scalar and vector. Oh, do you have plus is defined between scalar and vector? 박한솔? Like for example, C is scalar, then it's vector. Is it possible? It's illegal, right? It's different things, different animals, right? How minus? Obviously no, right? How about multiply? That's already defined, right? How about division? Division is a little bit tricky, right? We don't have any C, right? But the other way around, this one is defined, right? This is more or less multiplication, right? Well, we can always say, okay, only multiplication is defined. And I say, okay, there's another way to see multiplication. Then, how about among vectors? Yes, plus is defined, right? You can add plus. Minus is also defined. How about division? Have you seen any division of vector by another vector? No. No such things. How about multiplication? Yu Hyung-wook, have you seen any multiplication of vectors? Similar, right? But they never call it multiplication, right? They somehow, rather than using multiplication, they use what? Product. Looks like the same, but it's different. Also in the product of vector, 2 types of product are defined actually. One is inner product, sometimes called vector dot product, because usually this is mathematical notation, they use dot. They call dot product or inner product. What's another type of product? Outer product. So I don't know, this is what you do? This is defined. Actually, in our case, we can ignore that. Why? I say we can ignore that because we are computer science student. If you are student of mechanical engineering or electrical engineering, yes, there's some applications you have to worry about this. In our case, no. Like in this case, electric field and magnetic field, when they interact with each other, then how to come up with derived force. In that case, they use this outer product or cross product. But in our case, actually, we don't use this. Let's see. What's the geometrical interpretation of this inner product? For example, this is axis, right? I'm saying this one product called this U, this V. What is this? 이상욱. So what's the output of this inner product? Scalar or vector? Scalar, right? This output is scalar, right? In this diagram, what's the meaning of this scalar? What does it represent? 하준수. What's the meaning of this? Can you speak up? Let's think about this. What is you? Okay, go back home, then look at some of the old books. Because in the most cases, you should simply memorize. Okay, that's not enough. When you have such a notation in certain context, what does it mean? 지영탁, when you come with dot notations, cross notations, why did they come up with such a notation? Simply for fun? As they said, oh, I have this phenomena, these modeling issues. So they needed that, right? Then what's the first application of this in the product? What's the first application of cross product? How do they use that? Until you understand or come up with such an example, actually you do not appreciate mathematics at all. Actually, you can take an exam, but you don't have any chance to use them. Okay? So this is bottom is more or less you already know that. So this is where we can compute using this inner product. The other one is okay. You can this another way to present is okay. This is using column vectors. This is most linear combination. This is another way to see it. But when you try to see this first representation, it's much easier to understand, right? Even you don't have to worry about what the inner product is, right? Oh, that's easy. That's just linear combination, right? So you don't have to worry about this, right? Basically same concept. So here actually, I try to introduce some concept which you may know already or not, rather than just explaining all this computation. So we know what is vectors, right? We assume we have three vectors, U, V, W, right? So we can combine them, just combine them, right? Let's talk about it. We just combine only vector U with X for all X1. So what does it constitute? It's U vector. Then multiply by X1 for any values of X. 강은서. So what is it in that case? 양승호, what is it? Here is X value is when they say okay, this is from minus infinity to plus infinity, right? So this is U, right? So it means this line, right? This all the point of this line, actually this one actually means this line, right? How about second one? Like this one. This is more or less the two vectors, right? When you see the U, V, two vectors, can you imagine plane which include two vectors, right? So basically, this one is plane, whole plane, which include both U and V. So any point on the plane, you can represent as a linear combination of two vectors, right? So when you have all three of them, this whole space you can represent, right? So this is case. Here is one issue is assuming U and V and W are independent. what happens actually, rather than using this W, you're using this W star, which are different. When you combine, like for this equation with W star, what happens? Can you notice one is U, V, and W? Here is basically what is what is U times V. When you add them up, what is it? Let me see. Then how about U plus V minus W? Let's see. This is 0, 0, 0? This W star. I'm sorry. Right? What does it mean? They are linearly dependent. So when you add them up this way, it doesn't cover whole space. It covers some spaces. Okay? What's time? Okay, we have 30 minutes. Let's come up with this matrix. This is matrix A. Okay, then is AX is B. Then is when you AX, then compute this, right? Right? So when you plug in whatever this, if you know the value of X, you can easily compute the value of B, right? So basically here is what I'm saying is AX is B. So when you move forward, it means compute this way is pretty easy, right? So whatever number you plug in X, you know the values of B, right? This fourth computation, you already know that, right? So this is the fourth computation. How about the other way? I have a value like AXB, B is given, so I need to find out X. So basically, so two issues. One case is I just given value X, I try to compute the B, it's easy, right? Sometimes I say, okay, value is B, I try to find out X, right? So this is more or less, say, reverse computation, which is solving the problem. But, I'll discuss it later.
Professor,
Yes.
저거 상사 정사 확률에서 역행렬 구하는 방법 저희가 알아봐야 되나요?
That's the things we discussed in the class. No, you'd have to. So here is basically you try to understand what I'm trying to say. Techniques, don't worry. Even Gaussian elimination, don't worry. Okay? Let's just move another area completely because here is, why should I learn these things? Okay, let me think of just one example here. What's this? Have you heard about color space in physics? No? Kim Young-jin, have you heard about the color space? Then have you heard about the primary colors? Samcheon, 삼원색? I don't know. Right? Probably this is very good example for space. Primary color, right? Two types of primary color. One is additive, the other is subtractive, right? What's the primary color for color television? 가준수. What's the primary colors for color television? What's 삼원색 for color television? 이상욱, do you know that? RGB, right? So RGB. Here it says, okay, using RGB, you can come up with any colors, right? So it means basically in a way like this. What is linear combination, right? By combining these three colors, you can come up with spaces, all the colors, right? If you are not able to come up with such a colors, you are in trouble. For example, you bought color television, LCD panel. Somehow, blue was broken, right? Then only combination you have is this, right? So you can produce only colors which can be represented by this, right? 선형대, understand that, right? So this is the only combination you have, right? But unfortunately, this color space says this is RGB. But when you see visually, you can see more than that actually. This is a very simple modeling. This says, okay, this is all the color systems. By analyzing them, rather than, with three color code, I can represent all the colors within that triangle. Okay? Like 형광물질, whatever. Like whenever like red is not real red. Okay, OLED or LCD. Actually, so depending on the company, some company has this point, that point, then coverage is narrow, right? Or you can now barometer, you can make it bigger than. Okay, but still, only linear combination, you can represent point within the triangle. What happens outside? 김효찬. Whatever this color is actually was, this is what point which you can visually see, but no way to present in video camera. Because what you can see or what camera represent is different. Camera only represents subset of colors you can see. So this is a whole color space which humans can differentiate. But this triangle, even this video camera, they have whatever these 3 points. Using that, they can only represent colors in that triangle. Okay, so they cannot introduce colors in this area. So I showed this diagram here, right? CMYK. What is CMYK? Yeah, see the magenta, yellow. What's K? It's black. Somehow they just call key. It's black. Why do they use K? It says, oh, we learned out only 3 colors, right? So 3 colors can represent But here is 4 colors, right? When you buy a very expensive printer, sometimes they have 12 colors. Oh, sorry. This is calling for lunch, so I have to finish up early. Oh, sorry. So, for example, here we choose 3 colors, right? If you choose only 2 colors, okay, this point, that point, this is the point on the line. That's all you can represent. Okay, these 3. Now you can represent whatever point inside, but still you are not able to represent here. So how do you solve it? Oh, I like to represent more. Then what are you going to do? I says, oh, that's no problem. I got another color here, right? Then this, right? Then you can represent more, right? Oh, it's 4 is not enough. My printer is more expensive one, right? So I'm going to have another one here. So K is still, I have some problems with representing black well. So that's why they introduce another color K, black, for. So basically, this is more or less linear algebra problems. For this point, now you have to combine them, right? Right? But in this area, you may have some multiple ways to represent. But this is the way. So whether you're going to have some 2-dimensional, black and white is basically just two-dimensional, right? Well, just 1 dimension, black and white, right? Just only 1 vector, right? Gray, right? For color, we have to come up with 3 bases. When you have problems with 3 bases, still we have a problem in representing black well. So they added another color like K here. Now still that's not good enough, especially when you see like advertisement copies. The color is not vivid enough. Then they says, okay, are you going to add more colors and more bases, then just combine them. So this is basically issues of linear algebra. Okay. Rather than continuing my discussion, okay, I just add just one more concept of I'm asking you a question. Have you learned about space or field in high school? Have you learned about the space? Probably you 공간. No. So have you heard about the closed? Have you heard about such a terms in high school? So what is closed then?
no change energy or
Oh, that's a physics problem. Here is more mathematics. Okay. For example, is integer. You know, it's a set of integer, right? Whole set of integer, or field, or whatever, right? Space, sometimes called integer. On the addition, 기억자. what is this? So what do you mean by set of integers closed under addition operation? Here is actually from integer, pick any integer I and j, right? When you add them up, this becomes whatever result, right? This is also integer. That's closed. That stays closed, right? How about then I divided by j? No, right? It's not. So result is not integer, right? Then so all those concepts here actually. So in vector, so here is your called a subspace. Like for example, from subspace, here is whatever linear combination of vectors in the subspace. And so any linear combination, right? Basically, this is more or less closed. So basically, you can say the subspace is closed on the linear combination. Means within one subspace, you just say, okay, this is whatever V1 or V2, whatever. So it means Vi, whatever alpha I for all I. So still whatever result you come up with, still it belongs to the space. So that's closed. Okay, I'll discuss this one later. Okay, let's start my class. So please ask questions. Most of the content you discussed today, actually, most of the things actually you already learned in high school. Now we just try to represent a little bit differently just by tweaking it. Okay? So here actually is all the computation, calculation, you know that. But here actually, how do I present? Still, I try to avoid the formalism as much as possible. Still, you have come with, okay, what's the vector space? Then what's the row space? Oh, that's the way I can see that. Or column space, oh, that's the way I can see that. So even when you have linear equations or matrix notations, oh, when do I have solution? Where I don't have solution? When I have some multiple solution? Just think about such things. So I revisit these issues later and later. Okay? 이성태, any questions? Okay. Let's stop. See you next week.